Okay, we start today's lecture. In the last lecture, we introduced what is a martingale. So for a martingale, first we have a filtration Fn. This is an increasing family of subsegment algebras of the whole space. And then for a sequence Xn, it is a martingale if and only if so roughly speaking, given all the information up to time m, we calculate conditional expectation of a future random variable, then it is given by the current state. So this is the rough idea for martingale. And for sub-martingale, we just replace equal sign by greater than and the super martingale by less than. So a quick way to remember which is super and which is sub is, for super martingale, the expectation is decreasing. And for sub-martingale, for sub-martingale, the expectation is increasing. And in the last lecture, we also introduced what is the optional stopping theorem. So in the optional stopping theorem, the goal is we want to derive whether we have, so for a martingale, we know that the expectation of the sequence is a constant. And for optional stopping theorem, we want to replace this fixed integer by a stopping time and see whether we still have the expectation of this x at a stopping time still equals the same constant for the whole sequence. And in optional stopping theorem, we have 4 criteria to check whether this is true. So this is not always true. We need some restriction on the stopping time or on the martingale itself. So this is what we did in the last lecture. And today we will talk about Martingale convergence theorem. So today we will discuss 3 different notions of convergence. So first, almost sure convergence. So in fact, the proof of almost sure convergence will be in the recitation. And then convergence in LP for p greater than 1. And finally, the convergence in L1. And in fact, after we know the convergence of this sequence, the next natural question is, so for martingale, we know that the expectation of the sequence is constant. And after we know that this sequence will converge to some limiting random variable, the natural question is whether we can replace this fixed integer by infinity. So this is the 4 topic of today. So first, 3 notions of different convergence, and finally discuss whether we have the expectation of the limiting random variable still equals the constant for the whole sequence. Okay. So first, we introduced several different notions for convergence. So for a index p greater than 1, first of all, we define LP space. And LP space is the family of random variable such that the random variable has finite p moments. And in this space, we define a p-norm. In this way, and we can check that this is a norm space. So the norm satisfies triangle inequality. So this quantity gives a norm on this space, and then this space is a norm space. And since this is a norm space, we can discuss what is the convergence in this space. So for p greater than 1, the convergence in LP is just a convergence with respect to this p-norm. So in the remaining of the lecture, if I write xn converges to x infinity in LP, then it means that it is converged under this norm. So it means that the p-norm between xn and x infinity goes to 0. Okay, so this is the LP space and the convergence in LP. So our first lemma, for p greater than 1, we know that LP space is containing L1. So this meaning that if a random variable has a finite p moment, then it must have a finite 1 moment. So the proof for this lemma is quick. It's just a Holder's or Jensen's inequality. So by Jensen's inequality, we know that the 1 norm can be bounded by the p norm. So if x is in LP, then of course it is also in L1 because it has a finite 1 norm. And a consequence of this lemma is if we have convergence in LP, then we have convergence in L1. And this is also because of this equation, inequality. So if we know that the sequence Sn converges to x infinity in LP norm, so the right-hand side converges to 0, and it implies that the left-hand side also converges to 0. So convergence in LP also implies convergence in L1. So this is a quick relation between different notions of convergence. And today we will discuss 3 different notions of convergence. First, for the Martingale. We will discuss 3 different kinds of convergence. First is the almost sure convergence. And the second, we will check under which condition that we have convergence in LP for p greater than 1. And finally, we will discuss when we have convergence in L1. So in fact, so this is 3 notion. The different relation between these 3 notions, we will see later that in order to get an almost sure convergence, it is sufficient to say that the martingale is bounded in L1. So if the martingale is bounded in L1, then we have almost sure convergence. For LP, the condition is if the martingale is bounded in LP, then we have LP convergence. But for L1, it is different. So for p strictly greater than 1, we only need to check that whether it is bounded in LP. But for L1, it is different. The condition is called the Martingale's uniformly integrable. And before we discuss the 3 notions of different convergence, for Martingale, we have the relation that is, so this is the weakest convergence. So for Martingale, almost sure convergence is the weakest one. And then we have L1 convergence. And then we have LP convergence. Okay, so this is the relation for the Martingale. So, and we will discuss them one by one. So first, almost sure convergence. The conclusion for almost sure convergence is, suppose we have a super martingale. So of course, you can also just remember this as a martingale. So suppose we have a super martingale that is bounded in L1. So bounded in L1, it means that the expectation of the 1 norm of all this random variable is uniformly bounded. So if Xn is a super martingale bounded in L1, then we have almost sure convergence. Then the sequence will converge to some limiting random variable almost surely. Moreover, we also have that the limit random variable L infinity is in L1, so it has finite 1 norm. And I won't prove the theorem here, so you will see the proof later in today's recitation. So just remember that if a martingale that is bounded in L1, then we always have almost sure convergence. And also the limiting object is always have finite moments. A corollary of the sequence of this theorem is if we have a non-negative supermartingale. So non-negative supermartingale. For a non-negative supermartingale, we already know that because this is a non-negative supermartingale, we know that this expectation is a decreasing sequence. So it is always bounded by the expectation of the initial random variable. So of course, it is uniformly bounded by something. So if it is a non-negative supermartingale, we already know that it must bounded in L1. So by the previous theorem, we know that for any non-negative supermartingale, we have almost sure convergence. Okay, so this is the criteria for almost sure convergence. It is in order to check whether we have almost sure convergence, we only need to check whether the martingale is bounded in L1. So here we have two examples. This is the most common example we used during the lecture. So the first example, suppose Ci is an independent random variable with mean 0. And we define xn as the summation up to n. And in the last lecture, we already showed that this sequence xn is a martingale. And now, if we suppose that this sequence Ci has finite first moment as an infinite sum, so assume that under this assumption, then we can check that for the expectation of, so for the first moment of this of the random variable xn, it is bounded by the summation of 1 to n of the first moment of Cg, and then it is bounded by this constant c, which is finite. So here we see that this martingale xn is uniformly bounded in L1. Since it is bounded in L1 by the criteria for almost sure convergence, we know that this martingale converges almost surely to some limiting random variable. And here we can easily guess that this limiting random variable is the infinite sum of all this Cg. Here, in fact, we also have that this sequence is also convergence in L1 under the assumption here. So in order to see it is convergent in L1, we need to consider what's the difference between these two random variables. So the difference between xn and x infinity is bounded by the tail of this infinite sum. And since this summation is finite, we know that this tail will converge to 0 as n goes to infinity. So this implies that in this particular example, we have almost sure convergence, and we also have convergence in L1. Okay. So this is the first example. For the second example, we want to consider the product of an independent sequence of random variables. So we still have a independent. Now this is a sequence of non-negative independent random variable with mean equals 1. And we define Cn is the product from 1 to n of this sequence. And in the last lecture, we already checked that this sequence Xn is a martingale. And now we see that this martingale is a non-negative martingale. Of course, it is also a non-negative super martingale. And from the criteria for almost sure convergence, we know that for non-negative martingale, we always have almost sure convergence. And then for the limiting object, we know that it has finite expectation. And then the natural question is, whether do we have the expectation of x infinity equals the constant of the sequence? And we will solve this question later, so at the end of today's lecture. So in fact, this is not always true. We need some restriction on this KCIs. So under some certain restriction of KCIs, we have this equality. But for under other conditions on KCI, we don't have that. We have an inequality. Okay, so this is the almost sure convergence. And then we turn to, okay, so yeah, this is the question. So next, suppose that we have a martingale that is bounded in R1. Then we already know that we have almost sure convergence. And then the next question is, do we have x infinity equals x0? So do we have x infinity equals x0? So here we see that since we know we have almost sure convergence. And in fact, if we have convergence in R1, then we have the inequality. So this equality is true. So star is true if we have L1 convergence. So that is why our next notion is to discuss whether do we have L1 convergence. But to discuss L1 convergence, I will discuss convergence in LP for p greater than 1 and convergence in L1 separately. Because usually, if we can check the martingale have convergence in LP, then it implies convergence in L1. And if the martingale is convergence in LP, then it is easier to check. But when we don't have convergence in LP, we can still discuss how to decide whether we have convergence in L1. So the next notion is convergence in LP. So second part of today is convergence in LP for p strictly greater than 1. So first introduce two inequalities. They are called Doob's maximal inequality. So suppose Xn is a non-negative submartingale. And we define Xn star is the max up to time n. And the conclusion is so this is the Doob's maximal inequality. Okay, before we give the proof of this inequality, let us check what's the relation here. So if we just look at the left-hand side and the right-hand side, what we have is this is what we have from the left-hand side and the right-hand side of this inequality. So here we see that if we don't have this star, this is true for all non-negative random variable xn. So this is true for all non-negative random variable xn. And for the important property here is for non-negative sub-Martingale, we can replace this xn by xn star. So the left-hand side going from here to here, in fact, the probability can be increased a lot. Because here what we have is xn is greater than lambda. Here, xn star is greater than lambda can be much bigger than the probability here, because this is the max from time 0 to n. So this one is bigger than this one. And for some Martingale, we can also show that this bigger probability can also be bounded by the expectation of xn. So this is the tricky part for sub-Martingale and for this inequality. Okay, so how to prove this Doob's maximal inequality? So now we want to consider this event. So xn star greater than lambda, it means that the max after time n is greater than lambda. So if we define a stopping time, that is the first time of this sequence to greater than lambda, then we can see that xn star is greater than lambda is equivalent to say that this stopping time is less than n. So we overshoot this lambda by some time that is before n. And then let us check what's the middle of this inequality. So now we already know that this event, xn star is greater than lambda, can be replaced by the stopping time is less than n. And now we divide the event according to which is this stopping time t. And now we take conditional expectation at fj. Since the stopping time t equals j is measurable with respect to fj, because this is a stopping time, so we can put this indicator function outside. And then because this is a sub-Martingale, we know that this guy is greater than xj. So we have and here we see that we are already pretty close to the left-hand side here. So t equals j. T is the first time that the Martingale is greater than lambda. So if t is greater than j, we already know that this xj is greater than lambda. So we switch the summation and expectation. What we have is so now we already showed that the left-hand side is less than the middle part of this inequality. And here, from the middle part to the right-hand side, it is immediate. Because xn is a non-negative random variable, we put an indicator function here. It is always less than without this indicator function. Okay, this is Doob's maximal inequality. then we can prove the second Doob's maximal inequality. So in the second one, we relate the p-norm of the maximal quantity to the standard one. So the same assumption, Xn is a non-negative sub-martingale. And Xn star is the same, is defined in the same way as before. And here we are interested in the p-norm of the sequence. So the conclusion is so this is the conclusion for Doob's maximal inequality. So before we prove this, we know that this Xn star is the max from time 0 to n. So of course it is always greater than Xn. And in fact, we know that, of course, we have the p-norm of Xn is less than the p-norm of Xn star. But this equality shows that even though this Xn star, the p-norm of this guy will be greater than that one, but it can also be bounded by a constant correction of the p-norm of Xn. And this constant correction corresponds to p. And here we also see that y, there is principal difference from LP to L1. So if P equals 1, then we don't have such a relation here. Okay. So second Doob's maximal inequality. Now we consider the p-norm of Xn star. So we need to calculate what is the p-norm of Xn star. A quick recall that so this is a equation for integral of polynomial for p greater than 1. And here we just replace this Xn star replace y by Xn star. So clearly we have so I have done nothing. I just write Xn star to the power p in another integral form. And then we want to switch the order of expectation in this integral. So in order to be more precise, we put an indicator function here. And then we switch the order of this expectation in the integral. This is after we switch the order of expectation and the integral. And then from the previous Doob's maximal inequality, we know how to evaluate this probability. So this probability is less than this probability is less than the expectation of Xn restricted to this event, normalized by 1 over x. So this is what we have from the first Doob's maximal inequality. And now let us check what we have in this integral. So I put this 1 over x to p minus 2 here. And then we switch the order of integral and expectation again. Minus 2. And so here the indicators for x less than Xn star. So we put this indicator function here. This is the same. And now we calculate out what is this integral. And here we also see that this integral equals this guy also depends on p is strictly greater than 1. So I just put this constant outside the expectation. And then for the product of these two, we apply Holder's inequality. So now we rearrange what we have now. What we have is we start calculating the expectation of xn star to the power p. And by applying once the Doob's maximal inequality and once Holder's inequality, what we have is so here we see that the, the left-hand side is the p norm of xn star to the power p. And the right-hand side is the constant times the p norm of xn times the p norm of xn star to the power p minus 1. So we divide this quantity to the both sides. What we have is the p norm of xn star is bounded by a constant times the p norm of xn. Okay, so this proves the second Doob's maximal inequality. Okay, now we can discuss the convergence in LP. So this is the conclusion for the convergence in LP. Suppose Xn is a martingale. And the P, we fix some P that is strictly greater than 1. Then the following three conditions are the same, are equivalent. First, the sequence Xn is bounded in LP. Bounded in LP. Second, we have almost sure and convergence in LP. And finally, we know that this Xn is the conditional expectation of some random variable z up to the time n for some z that is contained in LP. Okay, so before we prove this theorem, here we see that if we want to understand whether the sequence Xn is convergent in LP, we only need to check that whether it is bounded in LP. So if it is bounded in LP, then we have the convergence in LP. And of course, if we have convergence in LP, we also have convergence in L1. And the convergence in L1 will imply that x infinity has the same expectation of x0. Okay, so this theorem is the convergence in LP, and now we prove that 1 implies 2, 2 implies 3, and 3 implies 1. So how to go from 1 to 2? Now we assume that our martingale is bounded in LP. So bounded in LP means that the expectation to the power of p moment is finite. So we define this as some constant that is finite. And then, so since it is bounded in LP, we already know that it is bounded in L1. And since it is bounded in L1, we know that we have almost sure convergence. So we already know that we have almost sure convergence, and then we only need to prove that we also have convergence in LP. So how to show it is convergent in LP? Okay. And to show the convergence in LP, we will use Doob's maximal inequality. So define yn star is the max from time 0 to n, but for the absolute value of xk. So xk is a martingale. Absolute value of xk is a sub-martingale. And since this is a negative sub-martingale, we can apply Doob's maximal inequality. So here what we know is and since we know that the sequence xn is bounded in LP, C, okay, and it's finite. So now we can also derive that the sequence yn star is also bounded in LP. And then by Doob's maximal inequality, oh no, so this is Doob's maximal inequality, and then we see that this yn star is an increasing sequence because it is the max from 0 to time n. Of course, this is an increasing sequence. Since it is increasing, we know that we can define its limit. And this is an almost sure limit. And then by Fadou's lemma, we know that this yn star also have finite p moment. And it can be bounded by the same constant here by Fadou's lemma. Okay, y infinity, sorry. And then let us go back to look at the sequence xn. So xn, we know that, of course, it has to be less than yn star. And this yn star is less than y infinity star, because y infinity star is the increasing limit of yn star. So now we see that xn is bounded by y infinity star, and y infinity star is contained in LP. It has finite p moment. Now we can apply dominated convergence theorem. And this implies that our sequence xn converge to x infinity in LP. Okay, this is going from 1 to 2. So from the case that X is bounded in LP, we can prove that we have convergence in LP. And here the key point is we use this maximal inequality to derive a bound in LP for the sequence. And then we can apply dominated convergence to show that the sequence is convergent in LP. Okay, so this is from 1 to 2, and then from 2 to third. So the second condition says we have almost sure and convergence in LP. So assume that Xn converge to X infinity almost surely and in LP. And then we want to show that, in fact, this sequence Xn equals some random variable taking condition expectation up to time n. So here, in fact, we can just take z equals x infinity. So take z equals x infinity. And for the Martingale, we already know that xn equals xk up to the conditional expectation up to time n. So now, roughly speaking, we take k goes to infinity, and this implies that xn is the conditional expectation of x infinity given fn. So this is the rough idea, and now we prove this precisely. So why we can take limit in this way. So suppose we have convergence in LP, and now we want to show that, so we want to show that xn equals the x infinity taking conditional expectation up to time n. So in order to show this, we consider the difference between these two random variables. So the difference between xn and x infinity given the conditional expectation up to time n. And since the sequence xn is a Martingale, we know that for any k greater than n, we have xn equals the conditional expectation of ik up to time n. And then for the linearity of conditional expectation, we know that this equals xk minus x infinity given fn. And then we take absolute value to both sides. And then Jensen's inequality tells us this absolute norm can be taken inside the conditional expectation. And then we take expectation to both sides. So we take expectation to both sides. So it tells us the difference between this xn and x infinity up to n is bounded by the expectation of the one norm between xk and x infinity. And this is true for any k greater than n. So the left-hand side has nothing to do with k, but the right-hand side is it depends on k, and this is true for any k greater than n. And since we know that we have convergence in LP implies convergence in L1. So as k goes to infinity, this one goes to 0. So now we see that when we take this limit, this left-hand side has nothing to do with this limit, and the right-hand side goes to 0. This implies that the left-hand side has to be 0. So the left-hand side here is 0, and this implies that the quantity here is 0 almost surely. Okay, so this is from second condition to the third. So convergence in LP implies that we can rewrite the sequence of random variable xn. In fact, it's just a conditional expectation of the uniform random variable. Okay, so this is from second to the third. And finally, let's go to third to the first. So now we already know that the sequence xn, so there exists a random variable z in LP such that xn is the conditional expectation of z given fn. And we want to show that the sequence xn is bounded in LP. So we need to calculate with the p moments of the sequence xn. And we know that xn is the conditional expectation of z given n. So now we apply Jensen's inequality. So Jensen's inequality tells us we can put this p norm inside the conditional expectation. And then we take expectation to both sides. And the right-hand side becomes the p moments of z. So here we have shown that for this sequence, it is uniformly bounded in LP. Okay, so this is from the third condition to the first. So now we have completed the proof that all the three conditions are equivalent. And then from this theorem, we know that if we want to show that the sequence is convergent in LP, it is equivalent to say that we need to check whether it is uniformly bounded in LP. So if the sequence is uniformly bounded in LP, then we have convergence in LP, and convergence in LP implies convergence in L1. And since we have convergence in L1, then we know that the expectation of x infinity equals the expectation of x0. Okay, so this is the convergence in LP. And the next question is, so in order to have convergence in LP, we know that it is equivalent to say it is uniformly bounded in LP. But what happens if we don't have uniform boundedness in LP? So this tells us we still need to consider whether we have convergence in L1. So before we go to convergence in L1, just one quick example of convergence in LP. So in this example, again, this CI is an independent sequence. And now assume that we have finite second moment. And we define our martingale in the same way as before. So xn is the summation from 1 to n of Cj. And we already know that this is a martingale. And now we assume that we have this finite expectation, a finite second moment. Then, in fact, we can check that this xn is uniformly bounded in L2. So why this is true, we need to calculate with the second moment of xn. So what is the expectation of xn squared? So xn is the summation for j from 1 to n. And we know that if we expand this square, so if we expand this square, this is what we have. We have diagonal term and the term outside the diagonal. And now, because we know that this Ci, they are independent, and each of them have mean 0. So for this term, if we take expectation, it will give a 0. So the only remaining term is the diagonal term. And here we know that this sum is bounded by this C. So this tells us the sequence xn is uniformly bounded in L2. And since it is uniformly bounded in L2, we know that we have L2 convergence. So since it is uniformly bounded in L2, then we apply the previous theorem. We know that we have convergence in L2. And since we have convergence in L2, we also have that the expectation. So of course, for the first moment of this expectation, it is 0 because convergence in L2 implies convergence in L1. And for the first moment, we know that the expectation of xn is always 0. So for the first moment of x infinity, it is always 0. And since we have convergence in L2, we also know that the second norm is also convergent. So at the same time, we also know that the expectation of xn squared equals this C, equals this infinite sum. Okay, so this is an example of convergence in L2. Okay, so going back to this convergence in LP, so in order to have convergence in LP, we know that it is equivalent to say this sequence is bounded in LP. And the next question is, if we don't have bounded in L2 in LP, then what should we do? So if the sequence, we can take the p norm of the sequence. If it is not bounded in LP, how we derive whether we have x infinity has the same expectation as x0? And then this gives us, and we know that in order for x infinity to have the same first moment as x0, it is equivalent to say convergence in L1. So we still need to decide whether we have convergence in L1. So this gives us the next topic of today is the convergence in L1. So now we have a break, and then we resume in 5 minutes at 10:15. So a family of random variables is uniformly integrable. And throughout my lecture, I will write UI for uniformly integrable. So this family is UI if So this is the definition for the family is UI. So what the rough idea here says, if we only look at the tail part of this sequence xi, so we only look at on the event that xi is greater than alpha, so this is the tail part of this xi, and then we take the expectation on this tail part, then this tail part is uniformly goes to 0. So this is the rough idea of this definition. And another remark is, here this I doesn't need to be countable. It can be any index family. Okay, this is the definition for UI family. Some basic properties. So first, a family of only one random variable is UI. So if x is L1, then the family of only this one random variable is UI. Because we know that for this only one random variable, this quantity will go to 0 as alpha goes to infinity. So if the family only contains one random variable, it is UI. The second basic property, if we have two family of UI random variable, then the union of the two is also UI. So here we can quickly check that if we have a family xi and another family yj, both of them are UI. So since both of them are UI, it means that for any epsilon positive, there exists alpha such that this part of the expectation restricted to tail is uniformly bounded by epsilon. And for the sequence yj, we have the same thing. So maybe another constant beta. So there exists alpha and beta such that this expectation restricted to the tail part is also bounded by epsilon. And then we take the union of the two, and we just take m as the max of the two. Then we know that the supremum of I and j is bounded by epsilon. So this tells us the union of the two UI families is still UI. Okay, next basic property is if the family is UI, then we have uniform bounded in L1. So a UI family is bounded in L1. So why this is true? Because we already know that the expectation restricted to the tail part is very small. So for any epsilon, we know that there exists alpha such that the expectation to the tail part is bounded by this epsilon. And then we can see that the expectation of this xi, we can divide it into two parts. The first part is xi less than alpha. The second part is xi greater than alpha. For the first part, of course, it's bounded by alpha. And for the second part, it is bounded by epsilon. So here we see that a UI family is bounded in L1. So if it is UI, we know that it is bounded in L1, and then we have almost sure convergence. So here, just an important remark is, a UI family is bounded in L1, but the converse is not true. So if we have a family that is bounded in L1, it doesn't imply that it is a UI family. The last basic property is, if a family is bounded in LP for some p greater than 1, then this is a UI family. So bounded in LP for some p greater than 1 implies that this is UI family. So why this is true? Suppose we have a sequence of random variable xi that is bounded in LP. So the P norm has a uniform bound C. And then let us check what's the probability of the expectation restricted to the tail part. By Holder's inequality, we know that this expectation is bounded by the P norm of xi times the probability to the power of 1 over q. And then for this part, so for the first part, we already know that it is bounded by a uniform constant. And for the second part, it is not difficult to bound this probability. So at least we know that this is the probability is bounded by the expectation divided by alpha. And here, the right-hand side, we see that this sequence is bounded in LP. So, and of course, it is also bounded in L1. So this guy is bounded by some uniform constant. And then the right-hand side tells us this expectation to the tail part is bounded by some constant, C tilde times alpha to the power minus 1 over q. And then we can take alpha big enough so that this right-hand side is less than epsilon, and this shows that this sequence is UI family. Okay, so this is some basic property of UI family. And the first non-trivial example for a UI family is given by this example. So suppose we have a random variable z that is in L1. And then we consider the following family. The family gives all the conditional expectation of z given A. A is a subsegment algebra. So this is a family, and of course, usually it is uncountable. And this family is also UI. So in this family, the random variables are indexed by the subsegment algebras A. And we put them together. Usually this family is uncountable if our probability space is a big one. So usually this family is uncountable. And for this family, we can prove that it is also UI. So why this is true? So the proof has 2 steps. For the first step, we're going to show that for any epsilon positive, there exists a delta positive such that So for the first step, we will show that for any epsilon positive, there exists delta such that the expectation of z restricted to this A is smaller than epsilon, as long as the probability for A is small enough. And then the second step is the conclusion. Okay, so first, for the first step, why this is true. We know that this Z is in L1, so we know that the expectation of Z is finite. And then, since it is finite, we know that there exists some number m such that the expectation of the Z restricted to the tail part is very small, say smaller than epsilon over 4. So as long as this m is big enough, we know that this particle goes to 0 as m goes to infinity. So for m is big enough, the expectation restricted to the tail part is very small. And then we can pick delta equals m over 2 epsilon. So this is some, So m epsilon over 2. 2m. So this is some strictly positive constant. And we will show that this delta satisfies the condition here. So as long as the event A has probability less than delta, then we know that the expectation of Z restricted to A is very small. So why this is true? So now we consider the expectation of Z restricted to A, and we divide this expectation to two parts. The first part is Z less than M. The second part is Z greater than M. Okay, so for the first part, since Z is less than M, the first part is bounded by M times the probability of A. And for the second part, it is bounded by the quantity that when we don't have this indicator function. So it is bounded by epsilon over 4. And here, because we choose delta in this way, and we know that the probability of A is less than delta. So this is less than M times epsilon over 2M plus epsilon over 4. And this is strictly less than epsilon. So this proves the first part. So as long as this event probability A is small enough, we know that the expectation of Z restricted to A will be very small. And then we can prove the conclusion. So why this family is UI? So in order to check this family's UI, we only need to check this expectation restricted to the tail event. So this Z given A is our random variable, and we need to calculate what's the expectation of this random variable restricted to the tail event. I just write this event outside A. So A is the event that this random variable is greater than alpha. This is the tail event. And now we want to calculate what's the expectation of this random variable restricted to this tail event. So first, by Jensen's inequality, we know that we can put this absolute value inside. This is by Jensen's inequality. Second, we see that this event A is defined in this way. So this is a random variable greater than alpha, and this random variable is something that is measurable with respect to A. So this event A is contained in this algebra A, because this random variable is measurable with respect to A. So this random variable is greater than alpha is also contained in this A. And since this is measurable with respect to the sigma algebra A, we can put this indicator function inside. And then we take another so we put this indicator function inside, and then we take another expectation. Then the conditional expectation disappears, just the expectation. Okay, so in order to see that this formula has very small tail expectation, we only need to prove that this expectation has very small expectation. And then we can apply the first part. So in order to say that this expectation restricted to A is very small, it is sufficient to show that we have we can choose an alpha so that the probability for A is very small. So okay, so to show the expectation restricted to the tail event goes to 0, it suffices to show goes to 0 as alpha goes to infinity. And by the first step, we know that this suffices to show this probability here goes to 0 as alpha goes to infinity. So from here to here, we use the calculation here. So in order to show this guy is very small, it is sufficient to show this guy is very small. And then by the first step, we know that in order to show this one is very small, it is sufficient to show that there exists a probability, so the probability of this A is very small. So it suffices to prove that the probability for the tail event is very small as alpha goes to infinity. And then let us check what is the probability here. So the probability for conditional expectation greater than alpha. So first, of course, it is less than the expectation of this quantity divided by alpha. And then by Jensen's inequality, we know that this absolute value can be put inside. And now we take first conditional expectation and then expectation. It will give us the expectation. And here we see that this guy will go to 0 as alpha goes to infinity uniformly over A. And this shows that the probability here, supernorm over subsegment algebra will go to 0 as alpha goes to infinity. And this implies that this family is a UI family. Okay, so now we have introduced the notion of UI family and several basic properties. And here, this is the first non-trivial property, non-trivial example for UI family. And then we can discuss convergence in L1. So convergence in L1. Suppose we have a martingale. Then the following three conditions are equivalent. First, the family is UI. Second, we have almost sure and convergence in L1. Finally, this xn can be written as the conditional expectation of a uniform random variable. Okay, so first, before we give the proof of this theorem, from 1 to 2, if this family is UI, we already know that it is bounded in L1. Since it is bounded in L1, we have already the almost sure convergence. So from 1 to 2, we only need to show that we have L1 convergence. And then from 2 to 3, we can repeat exactly the same proof as for the LP convergence case. So from 2 to 3, we can repeat exactly the same proof. And then finally, from 3 to 1st. So if xn can be written as conditional expectation of z given some subsegment algebra, from the previous theorem we proved, we already know that this implies that we already know that this family put together is a UI family. So this implies that xn is a UI family. So this is from 3 to 1. Is also known from the previous theorem we proved for UI family. So for this theorem, the only thing we need to prove is if the sequence is UI, then we have convergence in L1. Okay, is there any questions? So for this theorem, to prove these three conditions are equivalent, we already know that we can repeat exactly the same proof to go from 2 to 3rd as for the convergence in LP. And then for 3rd to 1, it is just implied by the theorem we just proved. So the only thing we need to prove is UI implies convergence in L1. So proof from 1 to 2. If the family is UI, then we have convergence in L1. So now we know that this family is a UI family. Since it is UI, we know that for any epsilon positive, there exists M such that the expectation restricted to the tail event is smaller than epsilon. So this is the definition for UI family. And then let us check why we have L1 convergence. So the idea is, since we know that the expectation outside this tail event, in this tail event is very small, and within this event, so when xn is less than m, we have dominated convergence in L1. So this tells us we should consider this sequence into two parts. One part is everything is inside this interval, then we have dominated convergence. And for the sequences outside this interval, we know that it is very small. Okay, so define the cutoff function So define the cutoff function as phi m. It is x inside the interval that x is less than, the absolute value is less than m. And outside this interval, it's just a cutoff by m and minus m. And then since the sequence xn converges to x infinity almost surely, we know that if we cut off this sequence, we also have convergence almost surely. And then for this sequence, cutoff sequence, we know that this cutoff sequence is uniformly bounded by m. So now we can apply dominated convergence theorem. So the dominated convergence theorem tells us this cutoff sequence also converges in L1. And since it is convergent in L1, we know that there exists a number integer n such that the difference between these two is very small after this n. And then we can go back to our original sequence. So for the original sequence, in order to show we have convergence in L1, we need to consider the difference between xn and x infinity. So now we divide this difference into three parts. The first part is this guy, so everything is inside this interval. And then the difference between xn and the cutoff, and the difference between x infinity and the cutoff. And for the first part, for n greater than big N, we already know that it is less than epsilon. And for the second part, xn minus the cutoff, it is bounded by xn restricted to the event that xn is outside this interval. So this guy is bounded by the expectation of xn restricted to the tail event. And here is the same. So this guy is bounded by x infinity restricted to the tail event. And we already know that both of them is less than epsilon. So this shows that the difference between xn and x infinity is bounded by 3 epsilon. And this implies that if the formula is ui, we have convergence in L1. So the idea is we cut off this sequence, and within this finite interval, we have dominated convergence. And outside this finite interval, we can use ui family and to show that the tail part is very small. Okay, so this is the theorem for L1 convergence. Here we see that the convergence in L1 is equivalent to say that we need to check it is a UI family. And here just a quick summary of this different notion of convergence. So what we know is, if we have bounded in LP, then bounded in LP implies this is a UI family. And a UI family implies that this sequence is bounded in L1. And here we also know that bounded in L1 implies we have almost sure convergence. And UI family is equivalent to say that we have convergence in L1. And bounded in LP implies we have convergence in LP. So here we can already see that this is the weakest convergence, and this is the strongest among the three. Okay, so convergence in L1. What's the next? Okay, so here just a quick generalization. For the first item, this is the conclusion for UI family. We know that if it's for UI martingale, if this martingale is UI, then we have the convergence in L1. And since we have convergence in L1, we have that xn equals the conditional expectation of x infinity. And now if we want to replace this martingale by super martingale, so everything is the same. The only different thing is we replace equal sign by greater sign. And if we replace martingale by sub martingale, just to replace equal sign by less sign. Okay, so this is about L1 convergence. And next, give an example. So now we can answer the question for this martingale, whether do we have the if x infinity equals the constant, equals the expectation of x0. Okay, so go back to this example. For this example, we consider a sequence of random variable that is non-negative, independent, and has mean 1. And we define xn is the product from 1 to j, and we already know that this xn is a martingale, and we also know that it is bounded in L1 because the expectation of xn is 1. So equals 1. This is true for all n, so this is bounded in L1. Since it is bounded in L1, we know that we have almost sure convergence. And then the question is, for this limiting random variable x infinity, do we have that the expectation of x infinity is also 1? So for the whole sequence, we know that the expectation is 1. And then for the limiting, so now we have almost true convergence. Then the question is, can we also take expectation to both sides and say that the expectation also convergent? So do we have the expectation of x infinity is also 1? And then we have a criteria for this question. So now we need to introduce another constant related to the sequence J. So the answer to this question is we have two different scenarios. So define Aj as the expectation of J. And by Jensen's inequality, we know that this Aj is between 0 and 1. And then the answer to the question is, we consider the infinite product. If this infinite product is strictly positive, then the answer to this question is yes. Whereas if the infinite product is 0, then we have that the limiting random variable is 0 almost surely. Since it is 0 almost surely, of course, the expectation is also 0. So the answer to this question is no. Okay, so this is the answer to this question, and you can easily check that with if you choose different Aj, you can have either cases you want. So why this is true? Okay, so after we define the sequence aj, we can define another sequence of Martingale. So if we define yn, so consider a new sequence. The new sequence is a square root of Cg normalized by aj. And then we know that this new sequence is non-negative sequence and it is independent and it's with unit mean. So and then we define the product from 1 to n and give us the yn. And we already know that this yn is also a martingale. And then for this yn, we can also check that it is bounded in L1. Because the expectation is always 1. Since it is bounded in L1, we know that we have almost sure convergence. And then, so this is the story about yn. And what's the relation between yn and xn? So here we see that the relation between yn and xn is, this is yn squared times the product of aj squared. So this is the relation between xn and yn squared, yn. And here we see that if yn converges to y infinity almost surely, then this part converges to y infinity almost surely. And if we know that this infinite product is 0, then this product goes to 0 as n goes to infinity. So here, in fact, we already proved the second scenario. In the second scenario, so if this infinite product equals 0, then we already know that xn converges to 0 almost surely. So this proves the second scenario. If the infinite product is 0, then the limiting random variable x infinity equals 0 almost surely. And then, of course, the expectation is 0. So the answer to this question is no. Okay, so next let us prove the first scenario. So what happens if the infinite product is strictly positive? So now assume that this infinite product is strictly positive. And we define yn in the same way. And then we define another sequence, is the maximal sequence of yn. And for this yn star, we know that yn star is an increasing sequence. And we denote its limit as y infinity star. So we know that this yn star will converge to y infinity star almost surely. And on the other hand, we know that the expectation of yn star, square. So the second moment of this yn star is bounded by a constant of the expectation of yn square. This is by Doob's maximal inequality. And then for the expectation of yn square, what is that? So it is, so we know that yn square is xn divided by this constant sequence. So yn star is xn divided by a constant. And the expectation for xn is 1. So the expectation for yn star, yn squared, is equals 1 over it equals a constant. It equals the infinite product from 1 to n and of aj to the power minus 2. And since we know that this infinite product is strictly positive, so this guy is bounded by some universal constant. So now we have shown that Yn star, Yn is bounded in L2. And of course, also Yn star is bounded in L2 because of Doob's maximal inequality. And since Yn star is bounded in L2, and Y infinity star is the almost sure limit of Yn star, we also know that this Y infinity star has a finite second moment. And then we can go back to the sequence xn. For the xn, we know that the relation between xn and yn is xn equals yn squared times the product. And here we already know that this yn squared is bounded by Y infinity square. And this guy is bounded by bounded by 1. So here we already see that xn is bounded by Y infinity star to the power 2. So this implies that and this tells us we can apply dominated convergence theorem to xn. Tell us we have convergence in L1. And since we have convergence in L1, we know that the expectation of x infinity equals 1. So the answer to the question is yes. Okay, so this is the answer to this question. So whether do we have the expectation of x infinity equals 1, and the criteria to check this infinite product, it is 0 or strictly positive. Okay, sorry, I will extend for 5 minutes to include everything for the uniform UI martingales. So the last topic of today is the optional stopping theorem of UI martingale. So quick recall of optional stopping theorem for ordinary martingale. For ordinary martingale, so recall, if for optional stopping theorem, we always want to consider whether we have the expectation of xt equals the expectation of x0. And for ordinary martingale, the optional stopping theorem tells us if we have 2 stopping time, so suppose xn is just a martingale, and then if we have 2 stopping time s and t, and they are bounded, so bounded, then the answer to this question is yes. And we also have that the conditional expectation of xt given fs equals xs. So this tells us for the definition of martingale, when s and t are fixed integer, we know this relation is true. And if we replace this s and t by stopping time, this is also true. But the condition is we need to assume that these two stopping times are bounded. And then now, for the UI martingale, if we require another condition on the martingale, so we require this martingale's UI, then we can remove the condition on the stopping time. So today, if we assume xn is a UI martingale, then for any 2 stopping time and s and t, so now we don't need to assume that s and t are bounded. So we replace the boundedness by this UI, then the same conclusion is true. And here, in fact, first we need to define what is xt. So what is xt? Because now, in fact, in this theorem, we don't require st is finite almost surely. It can be infinite. And when it is infinite, since this is a UI martingale, we have almost sure convergence. We know that we have x infinity, which is the almost sure limit of xn. And for this xt, even if this t is not finite, so it can equal infinity, then we can still define this xt. So the definition for xt is when t is integer n, of course it is xn. And when t is infinity, it is x infinity. So first, in this theorem, the definition for xt, so we don't require t to be finite. So even t is infinite, we can still well define this xt. So this is the first remark of this conclusion. And the second remark is, if you still remember how we prove the theorem here, so the first step is we need to show xt. So the first step is we show that xt is the conditional expectation of x infinity given ft. After we show this one, then we can directly derive this guy, because then xt, because we already know that fs is smaller than ft. So if this is true, then we know that xt given fs equals x infinity given ft and then given fs. And since we already proved that fs is smaller than ft, so we know that this equals x infinity given fs, and this equals xs. If we assume this is true, then it is also true for time s. So this is the second remark. So in order to prove this optional theorem for UI martingale, we only need to check that xt is the conditional expectation of x infinity. Okay, so proof of the theorem of optional stopping theorem for this UI martingale. So our goal is we show that xt equals x infinity given ft. So first, before we do this, we need to check that xt is integrable. So I will leave this part as an exercise. And then we need to show that xt is the conditional expectation of x infinity. So in order to show xt is the conditional expectation, we only need to show that for any a in ft, do we have so we only need to check that for any event a in ft, we always have this equation. So now, why this is true? Suppose we start from the right-hand side, and we divide this expectation according to different value of t. Okay, so here I've done nothing, just to divide according to different value of this stopping time t. And now, by definition of ft, we know that if a is in ft, then a intersect with t equals n is in fn. So the product of these two indicators is in Fn. So we take conditional expectation with respect to Fn. And since the product of the two is in Fn, we can put this product of the indicator function outside. And here, since our sequence xn is a UI Martingale, for the UI Martingale, we know that for UI Martingale, we have the last item. It is equivalent to UI. So we know that xn is the expectation of x infinity given Fn. So this one equals xn almost surely. And now we switch the order of expectation and the summation. What we have is this one equals xt times the indicator on A. So this shows the equality here, and this implies that xt is the conditional expectation of x infinity given ft. Okay, so this is the proof for the optional stopping theorem for UI Martingale. And finally, just a quick summary of what we have today. So first, we know that if xn is a Martingale, if we have bounded in L1, then we have almost sure convergence. If the sequence is bounded in LP for p strictly greater than 1, then we have convergence in LP. And finally, if x is a UI Martingale, then we have convergence in L1. And also for UI Martingale, we have the optional stopping time, we have optional stopping theorem. And in particular, for the UI Martingale, we have that the expectation of x infinity equals the expectation of x0. Okay, I will stop here.